मैं जब कुछ जब समझ ही नहीं है, तुमने कुछ काम ही नहीं ढंग से, जब कुछ सोच रहा, देखो उधर बताओ काली पट्टी, हाँ काली पट्टी दिख तो नहीं रही?
नहीं सर।
बस
यस।
कम से कम यहाँ रहा करो 20 साल पहले।
Can we have a huge round of applause to welcome ma'am? A very warm good morning to all the distinguished dignitaries, respected director, esteemed colleagues, and dear students. In science, progress begins with curiosity, but in civilization, progress stands on measurement. And for nearly 5 decades, since 1979, CSIR-NPL and PTB Germany have shared a partnership built on precision, trust, and shared commitment to strengthen metrology. This collaboration has not merely supported projects, it has strengthened capabilities, nurtured expertise, and quietly contributed to the growth of India's measurement infrastructure. And today, we mark another significant chapter in this enduring journey. We are deeply honored to welcome Professor Cornelia Denz, President of PTB Germany, a distinguished scientific leader guiding one of the world's foremost national metrology institute. And we also extend a very warm welcome to Dr. Meisner, Head International Cooperation Asia, whose role in fostering scientific partnerships across the Asian region has been instrumental in strengthening global metrological collaboration. We are delighted to have both of you with us here today. So I request Professor Cornelia Denz and Dr. Meisner to kindly grace the dais, and I also request our Director, Sir, Dr. Venugopal Achanta, to please join on the dais. Can we have a huge round of applause, please? Thank you, ma'am. Thank you, sir. And your presence on the dais today symbolizes not only our institutional leadership, but the coming together of two NMIs committed to advancing global measurement science. And in India, we begin important academic and scientific gatherings with the lighting of the ceremonial lamp. The lamp represents the triumph of knowledge over ignorance, clarity over uncertainty, and vision over limitation. In many ways, it reflects the very spirit of metrology, bringing clarity to measurement, certainty to systems, and confidence to innovation. So may I request our dignitaries for the lamp lighting, please? For the lighting of the lamp.
या कुन्देन्दु तुषारहारधवला या शुभ्रवस्त्रावृता या वीणावरदण्डमण्डितकरा या श्वेतपद्मासना या ब्रह्मा.
Thank you, ma'am. May this flame symbolizes the shared light of scientific cooperation between PTB Germany and CSIR-NPL, a partnership that continues to illuminate the path of progress in global metrology. And as a gesture of our deep respect and warm welcome, I would like to request our director, sir, to please felicitate Dr. Cornelia Denz with a bouquet of flowers. Sir, please. Again, I request our director, sir, to please present a bouquet of flowers to Dr. Meisner. Thank you, ma'am. Thank you, sir. And we are truly honored to have both of you with us today. And to formally articulate the significant contribution of today's event, I would like to request our director, sir, for the welcome address, please. Sir, please.
Good morning, everyone. Good morning, Professor Cornelia and Dr. Uwe, for accepting our invitation and coming here. So as we have seen yesterday, so there is a strong collaboration which has been, or partnership between PTB and NPLI, as NPL India is known. right? So this goes almost like 50 plus years, as we come to know from Dr. Neeta's presentation. So she went through all the annual reports and found that the first interactions we had was way back in 1971, right? So this is 55th year going on, like, so it's a long tradition. So I was telling Dr. V yesterday that for us, like, whenever I talk to our people, uh, when we say that, like, okay, some hybrid comparison is to be done or some calibration is to be done for traceability purposes, the first choice is always PTB. When PTB is busy, then they recommend some other NMI to us to go for, and that's how, right, the relation continues. And the most recent interaction which we had is, I mean, best example of the cooperation is the National Solar Cell Calibration Facility, which was inaugurated last month. So already, as Dr. Sushil says, like 8 samples have already been tested for both private as well as public sector undertakings. So this relation is only going to grow forward, right? And your visit really helps. And yesterday we met DG ma'am, and she was also very supportive. She was saying that, like, we should take this forward through a formal proposal through the international our ISTAD, right? So let's hope that we can take this forward so that mutually beneficial R&D as well as development activities and cutting-edge metrology facilities will come out of our interactions. Digital metrology is something which we are actually participating in, and PTB's leadership and the involvement and the opportunities which our people are getting to participate global events, both in trainings as well as in the DCC. So that's something which we acknowledge very heartily and humbly. Right. So we look forward to these more interactions. Your talk, we requested you, and you kindly agreed to focus on the newer activities, the futuristic activities which PTB is taking, active participation in. So this will help us learn as well as find opportunities where we can strengthen our cooperation. So we really look forward to your lecture today. And thank you very much once again for accepting our invitation and coming here. Thank you.
Thank you, sir, for your kind words. We thank you for your guidance, which has been instrumental in further strengthening the long-standing partnership between CSIR-NPL and PTB Germany. And it is now my distinct honor and privilege to request a visionary scientific leader whose work and leadership are shaping the global future of measurement science. The president of PTB Germany has been at the forefront of guiding one of the world's most advanced Metrology Institute through an era of transformation. Ma'am, your lecture entitled Metrology in Transition, Shaping the Next Generation of Measurement Ecosystem is eagerly awaited by the entire NPL fraternity. We look forward to gaining valuable insights into the evolving global measurement landscape and the emerging trends defining the future of metrology. With great respect and anticipation, I now request Ma'am to kindly deliver the special lecture. Ma'am, please. So shall I take this microphone or this one? If you want to stand here, you can use these, or if you want to move.
And this is already connected?
Yes.
Okay. Yeah. And is it here also?
Yes, it will be visible here also.
Okay, then. So I'll take it. So, thank you very much. Thank you all for your nice welcome, for having us both here invited to your institution, and I've seen yesterday so many exciting things, so many technically and advanced topics that maybe my contribution is only a small part to what you already do. So thank you very much for having us here and for discussing with you in our friendship, in our long cooperation, what we can do for the future. So you heard about the title, and it's about looking at the past and how we can then advance to the future. Let me see here. Maybe I have to switch it on. No, it's on. Yeah, now there is it. So we all know that methodology is really our base of trust. And we know that we do world-leading science because we have our defined units. We know that we realize the smallest uncertainty by all our measurements, and that traceability is a reliable means to advance. And so that's how we share trust for science, industry, and society. And this is since 150 years. And also in India, you have celebrated this. I have to. Where is the signal? It's there somewhere. Maybe I have to. Now you see it. It's also in India something that is rather important. So it's 150 years that we are looking at. And also, we think that we have to look for the future. What can metrology contribute? Maybe it's a long line. And in order to metrology is accepted, we need to do research on the one hand, but we want to support the industry, its development, its competitiveness, its strengths, and we enable change. So innovation is something that is inherent in metrology and that we contribute to society and to industry. And also, the role of metrology in policy advising is quite important, because what we do is that we realize evidence-based facts where then policy can take it over. So our research findings, our expertise, and our experience as metrologists are rather important to advance also trustworthy information in order to make political decisions. So this together is our base. And if you look more closer, when we look into research, we know that our research, because it's based on the units and it's accurate, comparable, and fair, we know that we do a lot. For example, looking at atomic clocks. On the other hand, we do a lot for economy. And robotics maybe is a good example where quality assessment, but also conformities and legal certifications, as well as international harmonized standards, are important. And also we look at legal facts, and at least in Germany, a very discussed legal instrument where PTB is responsible, let me see, it's a speed meter. And the speed meter is rather important. Where was it here? Oops. What happens now? Let's see it here. And the speed meter is something that is rather important. And this is a legal metrology. So for PTB, we have around 60% of our tasks are research, 30% are services for industry and legal metrology, and 10% is consulting and helping others in international activities to start off becoming also metrology partners. And if you look at the future of metrology, then people say, and also CIPM, the international metrology, says, we have to respond to evolving needs. And maybe we have to get smarter, faster, and more integrated. So that is the future. And this web page says that instead maybe of merely being in the background and being an institution that does everything in secrecy, maybe in the future we need to stand up and become a leader for predictive force of the future and helping to advance these topics that are emerging topics and challenges of the future. And that's been my talk about, to talk about these things. What are the transitions we need to tackle? One is about the challenges in climate. Looking at defossilization, that is everything what the world needs, and looking at decarbonization. So the route goes from efficiency measurement about substitutions up to net zero. And what is the role of metrology? Of course, the metrology can have a quality infrastructure and brings together these organizations that can measure and assess the quality and the efficiency of renewables. For example, focusing on energy storage and energy grids in order to make them stable for the future. Measuring climate variables and the ecosystem of circular economy. So metrology, with addressing society and economy, but also the environment, makes really a difference. And that is one transition we have to take. Another transition is that many of the new measurements we are looking at becoming more complex. So there is some complex sensor networks combined, for example, with emerging properties. hyper-connected, intelligent system connected to AI, and we need to find new measures in metrology to measure and assess them. And there is a sort of systems perspective. Now we look at systems, like here's a city of the future where a lot of different signals are there, different sensors for gas, water, but also for 6G and others. So we go to sensor networks, we go to digitalization, and we go to embedded data. And so we have to also adapt metrology to this field. And finally, the industry is also looking for new topics, and the industry is now in the fourth revolution, that is also connecting digital to conventional processes. Machines are networked, and there's use of data. But there will be new solutions about it, and Industry 4.0 is just on the transition to Industry 5.0, where there's human-machine interaction and others, and maybe a good sign that economy is important for these new fields is that in the EU, in January this year, together President Modi and Ursula von der Leyen made a first step for a free trade zone of these two countries, and this means that in this free trade, all these questions that Industry 5.0 should advance are rather important. So this is also how we can advance together. And that's my talk about. I want to start how PTB started in that field, also to look a little bit in the past, then go to quantum, to sustainability, and to the future, and talk about these fields. But let's start with the starting point of PTB. Because PTB is one of the oldest metrology institutions. It had been founded 1887 by these two leaders, Hermann von Helmholtz, who was at this time a generalist as a scientist. He was a physician, he was a physicist, he was a biologist and chemist, and he did a lot of inventions. For example, he invented acoustic, let's say, metrics in order to measure hearing, or measuring also the eye. And his opinion was that every basic research needs to have the view of an application. And Werner von Siemens, of course, was an industry person, and he had the opinion that the basic research will help the next generation of industry applications to strive and to come up. And so they both wanted to have a new institution, which would be an extramural, non-university institution where research, basic research, meets industry. And this was something quite new, a real innovation, because it has not been there at this time. There have only been universities. So the foundation of the PTB itself was quite innovative. And they said you need excellent science for economic progress. And also, maybe the most revolutionary about it at this time was to connect basic physics with engineering, which at this time in universities was completely separated. So with this innovation, they started off, and here you see a first painting of this original historical site in Berlin-Charlottenburg. And in 1900, it already has grown a lot. And the question, why was it grown? But it's still there today. And today we have this ground as one where we look at medical physics, where we look at innovation, information science, but we also look at combinations with temperature, with sustainability questions. So in a way, the actual question has been transferred also into that campus. And sometimes today we ask what they both would do today. Which innovation would they take and how would they take? Because they are really strong examples from this time where they started early. Now, why had PTB become so famous from scratch? When Siemens was involved in this activity, he gave ground in order to build PTB, and he gave also the first money for the first building. But he said he has one condition. He wanted that the very new emerging field of electricity should be in the focus of working. And he had one request, because electricity was just starting as lighting in the village, in the city of Berlin, and this lighting was just substituting more and more gas lighting, but it was very dim and weak. So the question was, what was the best lighting? How could electricity be better? And so PTB went back to make a basic research. The ideal emitter is a black body emitter, emits as much as it radiates out. And they were making the experiments, measuring the spectrum of the emitted light, and also trying to make a theory, especially Wien made the theory, and also there were people in Cambridge doing the same. But theory did not match the experiments, so as there was already starting a tradition to cooperate with universities, they asked young Max Planck, who was at the University of Berlin. And Max Planck, you know, just wrote the formula, or invented the formula that describes this black body experiments, and in Planck's formula there was Planck's constant. So quantum physics was somehow born, by a industry question transferred to a fundamental question, and then combining experiment and theory. And this is something that was giving the breakthrough for PTB as an institution. Nowadays, we still use black body radiators to calibrate instruments, especially spectrometers, that go into the atmosphere to measure essential climate variables in the lower atmosphere or on satellites in the higher atmosphere. So black body radiation is still in the tradition and has been retransformed for a new topic at PTB. And with that invention, now a lot of things happened in the first years of PTB. For example, Meisner did the first hydrogen liquefier in Berlin. There was a Geiger counter. There was a scattering electrons and photons by Bothe. There was sharing bridge. There was new discovery of ionized radiation materials. Albert Einstein did his only experiment on the magnetic gyromagnetic effect at PTB, and there was also some other events. So at this time, then PTB was becoming established, and the idea, the innovative idea to have a non-university institution was sort of proved that this is a success. So the history went on that unfortunately there was a time of the Second World War and the prosecution of Nazis, of Jews by Nazis, which was very unfortunate also for research, because the research was stopped for this time, especially innovative quantum research. And after the World War, Berlin was a divided city, so PTB went to Brunswick, Braunschweig, and then but a couple of years later also the Berlin Institute was merged with it. And when there was reunification, also the GDR Institute was merged with PTB. So now we are one institution at Germany. And the last revolution was 2019, when our units have been defined by the constants and have been much better to be measured. So also we have a common legacy. We heard that we have a partnership since 1971, so more than 50 years. And I just selected some examples of how we cooperate. For example, there is a strong cooperation about the CSIR-NPL cooperation, coordinated by PTB and always hosted here at NPLE. For example, we had this, as we visited yesterday, this strong cooperation with photovoltaic, measurement of photovoltaic cells. A couple of years ago, 2024, the Consul General of India in Hamburg visited PTB and visited all the Indian colleagues that are also at PTB, which also shows that India and Germany also not only have cooperation between different locations, but also we have a lot of guests and Indian students and researchers at PTB. And then there's workshops, for example, for the Ganga projects that also brings us together. These are just some small examples, and we will see more throughout the talk. But these partnerships is something that really brings together our institutions, and PTB nowadays has 3 locations. It's 3 locations, one in Brunswick, 2 in Berlin. In Berlin, we also have a synchrotron notation that we do together with a synchrotron notation called BESSI, a large facility in Germany. We have 9 departments of metrology and 2 administrative departments, around 2,100 employees, then additional 230 PhD students and about 130 trainees. And our budget is also given by the Ministry of Economics and Energy. But when we want to do research, we ask for budget for research funding, as everybody else, in a competitive way. We also get some budget from our Ministry of International Cooperation for technical development and cooperation, and from our legal metrology, we have some revenue which we give back to the state in order to also show that the state gets an income from PTB. So when we now want to tackle these challenges I was addressing in the beginning, we have started to make it a sort of matrix structure. We have our 9 divisions from mechanics to electrics, optics, and so on that do the expertise, but we have matrix-like interdisciplinary activities on environment, on health, on energy, on quantum tech, on digitalization, or on systems, where there's interdisciplinary work. There's also work on projects for a limited time, and there's also the idea that together the expertise of the different fields foster these topics for the future. And just our government, when it was renewed, or the new government at the beginning of this year was bringing out some new concepts. And maybe before I tell that, the world's biggest problem, according to UN, is climate change. So climate change is among many of these topics, like climate and energy. And it was also some association to advance schools that said maybe institutions today are not agile enough, not quick enough for the challenges that are upcoming. So maybe we also have taken an example to be quicker. And our government has this as a sort of regulation today to say they want to be quicker. And that's why they had realized an agenda for research. And by chance, in this agenda for research, there's quantum, there's microelectronics, there's energy, and there's also coming to new fields that are emerging, like for example fusion, but also resilience and medicine and health. And you see, these are just our topics. So in a way, we are in the midst of these themes that also the government think is important. And we also in our cooperation address these topics. For example, when you look at fountain clocks, we have heard yesterday in the presentation that this is a rather important topic also here, that we looked at fountain clocks and very early, starting in the 70s, we worked together to advance these frequency synthesis for fountain clocks and the microwave resonance in order to realize here cesium fountain clocks. So this is one of the very early cooperations that nowadays is also in the focus of quantum activities. We also looked at the strengthening the quality infrastructure, strengthening quality infrastructure in the question of life cycle management. This also is an important topic nowadays. And of course, we work together in educating younger people, pupils and young people. And our colleague Ravi Fernandez was here in order to also teach a large audience of pupils in order to interest them for metrology, because they are the ones that will tackle the issues of the metrology together. So we have strong partnership together with a lot of different activities, and I only show a glimpse of it. Yesterday we've already discussed many of the very attractive topics where we can collaborate also in the future. So over the years we had a lot of guests at PTB and a lot of guests came here, and I think our culture of exchanging people is really the right way to also go to the future, because if people interact together on all levels, from the leaders together to up to the students, then we can together go to the questions that are really important. And you see 40 guests since 2014. This is really, we have the most guests from India at PTB compared also to other nations, and we are very happy to do so. You're always welcome to come to PTB. So now let's go a little bit to quantum metrology. Quantum metrology is, of course, introduced into PTB for a long time, but especially with the new units that we have defined by constants. All constants are related somehow to quantum. The second is related, of course, to the transition of the cesium atom at the moment. But if you have an atomic clock and can move it in the gravity field on the Earth, you can measure a lot of things for climate projection, melting ice, but also what are the resources in the ground or other topics that you can measure. The kilogram, nowadays, we measure by counting atoms in a silica sphere. And if you can count atoms, if you know how to analyze them by special spectroscopic methods, you can use them for other purposes. For example, to look at ions in batteries for energy transition. In the ampere, we measure the current as precise as with the electron or the resistance. But this is rather important now for power grids. So the new challenges are all connected to our quantum topics. And of course, the most important quantum topics are atomic clocks. And if you look at atomic clocks, we also have now an emerging development. From the cesium microwave-based clocks, we are now looking at optical clocks, at different transition elements. Like, for example, strontium lattice clock, ytterbium ion clocks. And our uncertainty grows smaller in the range of 10 to the minus 18, which means really that we get a precision, for example, for GPS or for geodesy, that we never had dreamt before. We come in the range of centimeters to measure differences in height, for example, and GPS becomes much more precise. We also can start to measure fundamental things, as the idea of PTB was in the beginning, and PTB has started to realize a nuclear clock, which is a sort of really paradigm change to go to the nucleus and look at transition in the nucleus. And for the thorium atom, especially thorium-229, it is possible to have an optical laser-based VUV excitation, which makes the idea of how to address a nuclear optical clock become reality in the future. Because former times people said you need accelerators to have these nucleus to be hit together in order to have the transition, but you see it's also possible with a laser. And that is something which is the future clock. Now we're looking for the optical clock, and this is something we do together. So as I said, an early comparison between time and frequency between PTB and NPL in 1979 already gave the way how we work together and can work together in future on optical clocks. The optical clock will come. The international metrology is defining it, and in the next years we will see which will be the frequency of a new optical clock. But up to then, we can still work on the future of different optical clocks. And this means that we can make optical clocks even now more compact. And we have realized, on the one hand, an optical clock that is in 2 racks, it's hidden in the racks, and is so robust that it can be transported, at least in Europe, for making comparisons. And now a company has taken it over to produce it, so optical clocks becoming a product either. We also have a transportable optical lattice clock where we can go to different regions in Germany, different heights, and making geodesy, as I said. And also we do, for example, integration on a chip, because integration on a chip means making optical clocks so small that we can really use them for everything in applications. Then there is the next generation of quantum technologies, microelectronics, quantum computers, and quantum communications that require control of quantum states. And we also use integration for it, for example, superconducting amplifiers, for ion traps, for computers, or for optical quantum communication. And these has, again, applications. For example, if we think of microelectronics going to microchips, then we have to inspect these microchips and their quality. And the quality is based on the lenses and on the laser for these big machines that do create chips in nowadays in the range of 30 nanometers. So this is done in Europe. So it's company Zeiss and Trumpf of Germany do this. And we inspect the mirrors and the quality of the mirrors to have the right precision for imaging in order to create microchips. We also look at quantum computers. And for this respect, we have a regional collaboration with industry in order to also get industry interested to build quantum computers. And we have discussed yesterday that we are striving together with India to have a quantum time and frequency fiber network, because when the optical clock is coming and want to disseminate this and bring it to different regions, then we need optical fibers with a high quality and low noise that sustains it. So that's what we're also doing. And then we have also collaboration in these fields that are connected to EUV optics and to the same measurement, for example, doing for space optics. And this is done together with X-ray and EUV optics in Berlin in our facility as a synchrotron radiation. Also here we have very strong cooperations, which I found very good, because synchrotron radiation is a traceable source that can measure a lot of things in materials, and that is a materials machine, which is rather important for future materials inspections. Also, some materials that are important for electrical current definitions are based on quantum. And the quantum Hall effect that is known with semiconductors is now merging to other materials, like, for example, 2D materials, and graphene is one that is already thought of being the next material for the transition of the definition of, for example, the resistance. But graphene is very difficult to produce. To have a large-scale graphene, that is difficult, a homogeneous area. So you can change from N to P conducting, which is better to be produced, which is one thing. Then the quantization can also be with lower magnetic fields. You can also think of creating graphene within resins in order to stabilize it more, and this can also be, and there's another solution, and this other solution says we look at materials that have an inherent magnetic effect so that we don't need external magnetic effects, and we can be used by room temperature. And this is so-called anomalous quantum Hall effect materials, mostly 2D materials with a certain symmetry, like topological insulation or pentos or Kagome lattices. And we have realized together with University of Würzburg such materials. And the vision is that with that material, we can realize then a quantum electrical independent realization of the Planck constant and the electrical charge. So we would have a university quantum electrometrology toolbox where we have independent measurement possibilities. And this is something that we are striving for. And this is also a European project where European metrology together looks at this effect in order to look for the next generation of quantum Hall metrology. So sensors in quantum can also be useful for medicine, because if you use magnetometers that are optically pumped, they can have very sensitive magnetic field detection. And one magnetic field detection that is important for our future of space technology is that muscles, if you are longer in space, change. And then you can measure the muscle activity with this optical magnetometer. You can make it tiny, and then you can also look, for example, at the brain and making brain measurements by this small magnetometer, putting it out of the brain and then measuring very small changes in the neurodegenerative activities. And this is something that is non-invasive, very easy to wear, and this is done by this magnetometer effect. So it's called non-invasive magnetomyography. This is all done together with industry, where we put quantum to the next step in 2 buildings in Berlin and in Brunswick, which we call Quantum Technology Center. We have the infrastructure to measure advanced industry-oriented quantum technology, but also invite industry to measure in our lab. So it's let's say a platform where industry can meet PTB. And we also have regional clusters where industry can be interested and work together, get the possibility also to build startups and to just make an ecosystem of industries that is interested in quantum. And this is done together also with university in both institutions. And here's some examples we do. For example, in Brunswick, we have rented an old factory building where now 15 startups from quantum scenes can start to build up their businesses, and we are supporting them and they can use our infrastructure. Even PTB itself has a new startup that is looking for quantum computing. And for example, in Berlin, we have a new infrastructure called Unite, a big cooperation between universities, industry, and research institutions in order to build education for entrepreneurship and build education for how to start up companies and to help them patenting, licensing, and building startups. So we promote especially startups and small and medium-sized companies which are not themselves are easily having the infrastructure from quantum. And also we have test centers like this Unite Center and platforms that are fostering the interaction between industry and others in quantum technology. So also we try to work together internationally. And I think our memorandum of understanding for this national metrology institutes in quantum is something that was rather important. And what we want to do together is putting our knowledge together from these countries and thinking of the next generation of quantum applications, and to make also some harmonized pre-standardization of these fields. And since this quantum is often connected also to calculations in high-performance computing and AI, we also make bilateral cooperation in Europe, and for example also with institutions in Germany working in AI. And maybe we can look forward in the future also to have cooperations with India in these fields, as we had the AI summit last week here and showing that India is a striving country in that field. So let's look a little bit at sustainability. So there's one goal that almost all nations have to become climate neutral in the future, depending on when and depending on to which degree, but the 1.5 degree limit is given by many nations. So in a way, we have to think of how does it work that we come to it. And one idea is to look at different renewable energies. And in Germany, the renewable energies are starting slowly off. So now 55% of electricity is renewable, but heat and transport are very low. And most is wind and sun. But for 2030, Germany has the idea to go very far, about 80% electricity from renewables. How to go there? And how to have quality in this process. And that's what PTB or metrology institution can do. They cannot build everything up, but they can have the metrology and the quality assurance and the standards that these things go properly. And that's what we do with some competence centers. But first, let me say that, for example, for wind energy, the development is very slow in Germany, but we see that it's thriving in India. For example, in Germany, we have about 150 gigawatt in land and 30 gigawatt offshore wind engines, but we want to have, 2030 is our goal, but we are now, for example, only at 9 gigawatt offshore. That is different with India. You also have the same goals, but you are going very much quicker than Germany into it. But in both cases, the wind engines for the future for more energy grows bigger and bigger. And these bigger ones, these large gears, need also to be quality assessed. And so wind metrology needs research and quality control. And in India, where now you have wind power about 54 gigawatts, and you're aiming for offshore for 30 gigawatts, you have the same games, the same goals in Germany, but you're striving much quicker to it. So it's good to put forces together and to think of it. So what we do, we have realized a competence center, wind, and let me show you, I think now the transparency is missing, but maybe I can tell it to you. We have a unique infrastructure where we have wind turbine measurement, where you have a big machine where you can measure torques up to 5 meganewton meters to do so. We can also have, for example, a look at how we can realize large gear measurement by interferometric measurements, and also we look at wind 3D measurements. That's what we do together. And we have also transmitted these ideas for policy recommendation, because in the German law, if you have a flight radar system and you have a wind engine, there was the expectation that the interaction is around 15 kilometers. And we measured it with drones. We measured the electromagnetic field of the radar and of the wind engines and found it's much closer together. So we made an evidence-based report on it. The previous Minister of Economics took it over and then decided to change the law to build more wind engines in these regions. And because we are not measuring this anymore, because the measurement is established, the University of Applied Science have taken it over with a new institute and now making this measurement with drones about electromagnetic fields in the air. So this is one example. Another example is photovoltaics. In photovoltaics, every efficiency part is money. And this is also true for India, and India has really a high potential in photovoltaics, and its aim in 2030 to have 280 gigawatts is even more than Germany is striving for. But it's rather important because efficiency means also a strong market. So there's a strong market behind it, and that's where we are looking for. And we have realized such a metrology center for competence center for photovoltaics, where we have an artificial sun as well as having an outdoor measurement of photovoltaic modules. And these photovoltaic modules are measured as you do it here with an artificial sun, but also to look at the differential spectral sensitivity, measure it also outside. And that is something what we are doing, and we are doing this together. I visited yesterday the center, which is very nice. And this measurement outside can be also a complementary measurement here that we can do together. So here are the different infrastructure. We have an artificial sun, we have the outdoor measurement, and something that becomes important in Germany is photovoltaic parks. Here's one at the roof at PTB in Berlin. And also what becomes very fashionable for houses in Germany, for flats, apartments with many stories, that on your balcony you have a photovoltaic cell. And these photovoltaic cells have so much increased that they now have a participation of 14% of the solar production in private households in Germany, which is quite strong. And here we have visited yesterday the excellent facility that is here now as a reference photovoltaic measurement unit at NPL. And it has been together with PTB. It was a pleasure to do so. And that is something that is rather important for our collaboration. If we have one instrument and we transfer it, then it is built again and renewed and has better features than before. And this is the case here. This instrument now is a highly excellent instrument with lowest uncertainties, and it adds upon the world-leading institutions. And it's a pleasure to do such things, making things that we have done before and making it even better in a transformation to another institution. And now you are here driving it and have one of the world's best measurements for photovoltaic cells. And this has also been connected with workshops together to introduce photovoltaic measurement to everybody in India. And this has been workshops together with technical cooperation. Energy transition is rather important in photovoltaics, and I told you already that cities of the future are rather important. And in cities of the future, most people live in housings where there's a lot of stories. And if you have a photovoltaic energy generator on photovoltaic panel on the roof, how to distribute it? And this was a question that we did together with the question of how to build smart cities. And what we realized, it was 2 houses that we have in a small city called Bielefeld. One house with I don't think 10 flats were classically structured, and the other one had photovoltaics on its roof. It has a heat pump in it, it has batteries to store it, and it had a sort of smart system to share it in between. So inhabitants could use this energy for themselves, could share energy between each other, could help each other when, at which time of the day to do it. And this sort of idea to have fair billing together with using regenerative energies is one example how we in Germany think it can be in the future, because most people living in apartments together with others, and if there's only one roof, how to share these renewable energies in an effective way and to profit from it. And this was this project which is very much loved by the inhabitants of this building. Now let's look at energy that is, what is the issue of energy? The volatility in Germany is from wind from south to north, or dark time of photovoltaics, given oscillating regenerative energy that you see here from January this year in Germany. So wind and solar is there. We have a little bit of water storage and fossil gas that should help to stabilize it. But also in Germany, if you put too much of these regenerative energies with volatility into the system, it can happen what happened in Spain last year, that there is a power outage due to extreme values that are incoming into the net. On the other hand, in Berlin, 2 times last and this year, there have been sabotage acts where the electricity grid was just, by some sabotage acts, being cut down. So the question is, how can we get solutions in order to make the grid stable, to buffer it, and to have solutions for this sort of resilient threat we have in the system? And of course, we're looking at hydrogen for it. Hydrogen is something that is in Germany upcoming, but not a strong topic for the moment. However, hydrogen has different issues. You have to see, where does the hydrogen come from? So it's a question about provenience. You have to the question, how is the hydrogen transported? That's a question of safety and explosion safety. And how is it used? This is a question of effectivity. Now we are realizing a hydrogen platform where all these 3 components are there, and where we're looking at different fields. And there was a release of the Indo-German hydrogen roadmap already a couple of years ago in 2024. And I think that's a good idea also to look together at new hydrogen topics. And yesterday we talked already about the provenience question and where does hydrogen come from and how can we use it, for example, efficiently for electrolyzers, filling stations or others. And this can be also a new collaboration. When we think of the hydrogen economy, there's different approaches to go. You can have hydrogen full 100% tubes, which Germany will want to build. This is called a first net of hydrogen. But when it comes to households or to industry, then there is gas nets, and the gas net should be used for hydrogen either. So it's mixture. And then there's biogas either. So but we are looking at test infrastructures, and we do that together with some companies for pure hydrogen, but also, for example, together with those industries that use electrolysers. And we have realized also a transportable pipe measurement for gas metrology in order to see if there's mixtures. How can a gas, for example, tube sustain hydrogen? What happens there? So it's purity measurement, conversion efficiency measurement, metering, and all these questions around that we are looking at in our hydrogen metrology platform. We're looking also at batteries. Batteries are rather important for storage of energy, but there's aging about it. There's a question about state of health, state of charge, state of safety. And especially the safety is something that's rather important, how to analyze when a battery goes over the edge and is run away. And that is something we are investigating, how you can measure it and prevent this explosion hazard. And we also, together with some infrastructure in Germany, which is called Battery Lab Fab. So it's a research factory. We work together in order to make measurements in the process of production to see the quality of batteries. And this is done, for example, with optical parametric magnetometers. Electricity stabilization, as we said, is a huge problem. And in Germany now the idea is to use, for example, high voltage direct current transmission systems. And this new transmission system is built, like in the right picture, but how to measure it? So we've measured and realized a mobile high voltage direct current measurement system, which is shown on the left side. But if you look at it, you see that it's really transportable. So we have a truck where we can put everything there, go there and measure it. And what we do is challenge the system by having, for example, non-sinusoidal composite waveforms and challenge extreme values and see how such a transformation unit works into it, and then making grid dynamics measurements in it. We also look, for example, at carbon storage, which is rather important for Germany for the future. And then the question is, how is the leakage in carbon storage, and how can you store it, and how can you use it? What's the efficiency? And we use it. We now start with leakage monitoring at PTB and also in the EU project. So what is with climate transition? In climate transition, we have a lot of activities that are connected to atmosphere. I told you something in the beginning, to land, earth, and ocean and water. And for example, we measure essential climate variables like aerosols. We have an aerosol measuring station, and we're also looking, for example, at black carbon, which is rather important in Germany. And here we have a cooperation because there's a PTB aerosol testing, and we have international comparisons. And because India could not contribute to the international comparison last time, we are now working together to make a common bilateral comparison on that. And that's something we look to it in the future. We look at minimal moisture on the one hand, because for pure hydrogen piping, this can be disastrous, but also because in moisture, in water, we have analysis methods where we have to go from the classical water measurement of oceanographs or river measurement to some traceable measurement, which we do with electrochemical voltage measurement. And then recently, we have gone to the mountains. At Germany, the highest mountain is Zugspitze. And in Zugspitze, there's a research station. In former times, it was a hotel. Nowadays, it's a research station. And we measure there, on the one hand, aerosols like black carbon. We measure the CO2, climate variables, but we measure also, for example, environmental effects with Newton data, because these are also carrying information. And because in this high location, everything is very there's very diluted situation, so the traceability is challenged to look at very tiny amounts of climate variables and essential structures. So what we do is they are measuring tiniest amounts and showing that we can measure this with traceability. So that is the idea. And the idea of the station is finally to acquaint data to make a digital twin of the Earth and look into the future how our Earth develops in terms of climate change. So our big project together with climate questions at the moment from the technical cooperation is to look at the water cleanliness of Ganges. And this is a project that is ongoing now in the second phase, and we come to the third phase. And I think it's a good example of success where not only NPLI and PTB, but also other institutions work together for a certain goal where metrology gives a path by the traceability of the measurement, and then also with others together come to an endeavor, for example, to measure a river and to look at the river and its cleanliness. So this is a long-term cooperation that shows how we can introduce other stakeholders by metrology cooperation. And you see here there's a lot of different activities, instruments that have been exchanged, but also stakeholder meetings where different stakeholders are working together. And yeah, there was also projects and workshops in Germany in order to see how can we explain the method of metrology to others that maybe later on are those that are monitoring water quality in the daily life and are responsible then for it. So how can we do measurement and monitoring in the infrastructure of different countries? Now let's come to the last chapter, and what are the transitions we are really facing for the far future. I compare this always what we have to do with this Dick Fosbury invention. So you know that before, high jumping was in a way that everybody got forward over the barrier. But if the barrier went higher, that was much more difficult. And then Dick Fosbury was thinking, what are the rules? What can I do? And he was inventing to jump with the back first, which made him jumping much higher than others. And I think that's the open attitude to think something out of the box and find a solution where maybe nobody else has come to it. And this is the idea how we need to tackle some of the questions that are really burning in metrology for the future. And one is digitalization. Digitalization is not about having papers gone to PDF, but having fair data that are used in a way that they're machine actionable. And that, I think, is rather important, so that we come to machine actionable data exchanges. That is digitalization. And for this purpose, our metrology needs to be digitalized in any aspect. Our institution needs to be digital, having, for example, no longer paper but electronic files. The SI needs to be digitalized, which is already on the way. So we have a digital SI reference framework in the international metrology. Then we need to have digital services like conformity assessment. We have to have virtual measurement in metrology with digital twins, and we have to have data quality. So everything that has to do with metrology has to be rethought. And I just want to show you some examples, but maybe the one example where we have worked together, we not that was that we together were on the stage where we were discussing what is a fair digital revolution and showing the world at this 150 years anniversary what is important about digitalization. I think that was a good example to discuss together how this can go forward. For us, it's important to realize the quality infrastructure in a digital way. You know about the quality infrastructure and all the players that are around. But for digitalization, what we first need having together a cloud that can be trustful for all these institutions, but also for industry. So we call this a federated cloud, where everybody can have its own space, but we can exchange between spaces and have a common agreement about the data. And then, if we have so, we can realize digital system of units from metrology, or digital certificates, or smart standards from standards. We have an e-attestation now in Germany from accreditation. There are digital nameplates from market surveillance, or for example, digital conformity assessment. So all players of quality infrastructure now goes digital, which means that we can have a direct digital interaction between all service providers, that we can seamlessly give that to industry. And that also we have an added value because it's secure and it's trusted. So trust also goes to the digital transformation. And that is something that we are doing. And this can also be read in English, how we realize this quality X, quality infrastructure for the digital era. I want to show just one example, which we think is a sort of flagship, how it works. If we want to show industry how important digitalization is, then we have to tackle these, what are the interaction with industry, which is mainly certification. Digital calibration certificates or digital conformity assessment. So we made them digital in such a way that industry can use them directly into their processes in a machine interpretable way. So there is no paper anymore. And this is so that some industry said, this is like an MP3 format change, paradigm change, because it's really a change in the industry process. And we have convinced pharma industry that is now completely changing it, energy industry, and now it's mobility industry. And from pharma industry, there's a leading manager from Boehringer Ingelheim who said what really the industry said. The digital quality infrastructure is not something they just love as much as they can do and do it, but they said it's such an advantage. Employees don't need to take a paper and type in the data of the conformity assessment in their machines. It's just digital machine actionable. And also, this is more productive, that time saves time, and also the employees can do much more advanced work to advance the company. And that's why companies like it. It really gives them efficiency. And this is how metrology can support also the striving of industry in that way. AI is also a topic that you know much better than we do now because we had the summit here. And I think from metrology point of view, it's two things. On the one hand, we can use AI in order to use it to advance our processes. And on the other hand, we have to have the task to have quality assessment in AI. So in the one hand, we have AI for metrology, and on the other hand, metrology for AI. And this transition is also connected to devices. And for example, 3D manufacturing is something where digital data are going in. In robotics, machine-machine interaction, machine-human interaction is there. And we do this together with a project with industry in Germany. And also in Europe, there are testing facilities for certain branches, for example, from advanced materials or for health, where AI has an important role for the product development. And this is done also there. So that is what we think. We have for the traditional metrology task, we have AI used to make metrology quicker, like conformity assessment or others. And on the other hand, the new topics, smart mobility, energy, digital medicine, or city of the future, need some assessment that AI is safe there. And that's what we are doing both. And I want to show you two things, but just remind you that also in the international metrology, we are caring for it. I'm leading for now a big new overarching topic that is called metrology and digitalization. It overarches all different CCs, So and what we are doing is also looking for AI, safe and trustworthy AI. And in 2 weeks, we meet again in Paris to discuss these questions and to have a look how can methodology assess AI in a general way. But how is AI used in methodology? And one characteristic where methodology can advance AI is not that we can realize a lot of different AI applications, for example, for image analysis. But here's an example where we have a question that comes very often in methodology. You have to have a megaparticle counting, for example, in exhaust of engines or others. And then you need to know the number of the particle and the size of the particle. And you can do this with a neural network, a machine learning, convolutional neural network, and find it out. But then you can think of PTB is responsible for measuring wood. In wood, you have the same images. You want to know the number of circles and the diameter of the circles, which are wood in this case. Or you want to know it in medicine for lipid-based virus detection. Again, number and diameter. Or you want to make blood cell analysis or look at black carbon particles. Always the same. So you can take care that one neural network and one application of AI can be used for different areas and can be harmonized between different areas. And this is a metrology task, for example. And others are how to raise the quality of AI. And the quality of AI has to do with explainability, it has to do with transparency, and with robustness. And these are some of the metrics we need to define in order to define the quality of AI. But how to measure a system that maybe you don't know what is inside because the algorithm is not revealed by a company? Then it's a black box, and you can use data as a sensor to challenge this black box. And if you have data that your metrology have assessed beforehand, either artificial data or data that are physics-based, and then you put this to neural networks, you can see by the answer of data and recalculating to the early data how the quality of the AI network is. And I think that's something where also data as a sensor is a new field we have to look for. And finally, when we look at systems, we have a lot of sensors that are coming together, physical sensors, maybe data as sensors, and then maybe one sensor can be very cheap, a very cheap sensor for measuring temperature or measuring pressure or something else. And the own sensor itself has maybe a high uncertainty, but together as a number of a network or as a swarming of sensors, they can be together more than one single uncertainty. It can be a very low uncertainty. And these principles of complex networks have to be introduced to metrology and, for example, for new uncertainty measurement. And this is something what we need to do. And also, if we have these large sensor networks, can one sensor help calibrating the other? Can sensors interact together to get new data? And these are all questions that are connected to that. So it's a new world of sensor networks that is coming, and where we have a lot of potential for new metrology into it. And we have looked at this in 3 different examples. And I just want to pick out autonomous mobility because I've already spoken a little bit of the city of the future. And what we are thinking there is that the sensors in autonomous driving are essential for safety of people and safety of the car. But sometimes some sensors do not react as they should. And sometimes these sensors are connected to AI that is reacting differently. And sometimes one sensor fails. And is there other sensors then able to take over? So what we do is looking at sensor functions. Then we have sensor test cars where we take away one sensor and have a look what happens with the other sensors and how the car is behaving. On the other hand, we have visual scenarios showing, for example, with monitoring tool cars, scenarios that are very seldom, extreme scenarios in the traffic, and have a look how the car reacts to it. So this is a sort of challenging the automized car. And then now we are in the way of realizing a new environment, a real environment, which is a sort of testing hall. And in this testing hall that has never been there by now, we have a crossing, because most of difficult, challenging questions for autonomous driving are crossings. And in this crossing, you can now realize weather. It's the one time where we work together with meteorology and make fog, make rain, make heavy dust, and then have a look how these different sensors react. We can also have avatars like other traffic participants, motorcycles, people walking or driving bicycles, and then have a look how the car reacts on it. And all these typical reactions are needed to be trained by a car, but happens in the realistic driving, not as before. So we are doing this together with the university, and this is connected to everything else we do in metrology for mobility. For example, looking also at the exhaust in combustion engines. We have realized a new lab for it. And this is also done together. As I told you, we're measuring together these questions of key comparison of particle measurement in exhaust of different gasoline engines. And because there will be a change in rule in Europe, this is also important for us to measure this now for gasoline. Also for autonomous driving, there's a question of how battery-driven cars are connected to it. Because battery-driven cars in Germany are widely spread now, and the question is, how can we measure them? And we realized the measuring system where we have a truck, and in this truck we have the whole measuring system for battery, and this battery goes then to a fuel, to a battery charging machine, and then we can measure it. And this is connected to quality infrastructure because everything in it is also connected, for example, to certifications in Germany. The next level is heavy truck drivers, heavy transportation that needs to have battery cars, and this is connected to autonomous driving. So we're looking at charging with connected to autonomous driving. And with that, I wanted to end my presentation. So I wanted to show you how challenges emerge and metrology can cope with it and has new ideas. So digital technologies help to solve global challenges. And we can do energy monitoring, we can have transition towards climate neutrality, we can have digital economies, and we can support industry in all these new things. And in fact, today we talk about digitalization, sustainability, but also resilience of our system. And these three together can be accompanied by metrology because it builds trust, it accelerates, and it increases resilience, sustainability, and digitalization. So I think you agree that metrology also for these new fields is an anchor of trust, and that we can, from quantum to energy, from digital to systems, we can have new fields where metrology can advance this research, but build trust for industry and help industry to enter into this field. And what we do at PTB is doing worldwide excellent research, being technology innovative, and have regional ecosystem to support this. And I think that is something that also in India is going on. So it's another way to work together. And maybe interestingly, it was recently announced that the World Metrology Day in 2026 has the new motto, building trust in policy making. And this also shows that maybe metrology has to end to be secretly behind the scenes, but come in front of the scenes and also building trust and science-based activities also in policy and showing how important it is that science and industry cooperation comes from metrology. So thank you very much. And we think that new people like you are here are the future of these different endeavors. And here are some examples of PTB people. And they all, together with us, think that PTB is accurate, objective, and passionate. And I'm sure you're also, and this is a good basis for future collaboration. Thank you very much.
Do you mind taking some questions?
Yes, of course. Yeah.
So if someone wants to ask a question, they can raise hands.
I'll start off. Just a quick question. I mean, about the green energies or futuristic energy sources. So is there any focus or interest in geothermal energy in the German scenario?
So there is interest into it. It's a strong regional dependence. So at the moment, there are small villages or regions that's put into it. For example, we have some islands in the northern part of Germany where you cannot put heat pumps into it because the electricity system would not sustain it. So they look at geothermal questions. And for some of the industry, it's also a topic. It's a question if you can dig deep. In some areas you cannot, then you have to have flat geothermal questions. That is more difficult to think of. But it's a topic. But if you see the percentage wind and solar, then there's biogas, and then there's water, and then it's geothermal. So at the moment it's only a few percent, but I think it will be rising.
Thank you.
There's a hand behind you.
Good morning, ma'am. Just I'm asking for that traceability, meteorological traceability for speedometer. How to traceable that speedometer?
I didn't understand the question. Can you repeat it? So it's about regenerative energies. Did I get it right?
No, that is for speedometer. Speedometer, they are used that during the vehicle move and that how the kilometer per hour is
I
taken.
think there's some echo in it. I don't get it. Maybe if you put it a little bit far away, sorry. The speedometers. Okay. Sorry. Yeah. And the question of speedometers is which one?
Yeah, meteorological traceability.
Yeah. So in Germany, the speedometer is legal metrology. So we're legally measuring these devices, and it's about measuring them typically with lasers or with some other electromagnetic waves. And then if for example, a customer is not satisfied with a measurement of a speedometer and goes to court, then PTB can approve how are the uncertainties for that measurement. And now there's a new development that says speedometers with AI. And these AI-based speedometers are based on cameras. But these are trained by having many pictures and then measuring the speed better and better. So then how can PTB define the uncertainty from such a speedometer in a reliable way? Because it might change by the training of data. And I think that is one example where speedometers change and legal metrology change. Because if you have devices that are connected to AI, legal metrology will have a different definition of uncertainty, which is rather important for some legal questions. So that was why I put speedometers there.
Okay.
Excuse me, ma'am.
Okay.
How digital twin and ISEC simulation is helping for vibration simulation, vibration metrology? Digital twin, you shown digital metrology.
Yeah.
So how it is useful for vibration metrology? Means simulations.
So simulation metrology, I think, becomes rather important. So for many things, we talk about digital twins more than simulation. So really building by data everything that is in this device or in this machine. And then, for example, for our wind energy measurement, in the wind energy measurement, industry gives us the wind engine only for a few days. So you can measure the torque and you can measure the dimensions, and then you have a data, and with this data you can extrapolate how this will, for example, change in aging. And then you have the possibility with this data to measure more than without the data. And so digital twins become important, and you're right, between virtual metrology and digital twins there is a sort of, let's say, smooth border. We would say a digital twin should reflect all the data and has a model that reflects all the parameters that are necessary. Whereas a virtual simulation can make a sort of mathematical model that is simplified from it. So that is our difference in these two.
Thank you.
But digital twins, I think, for the future will be rather important because companies will no longer be able to look at all these things. Or industry will not give us the instruments anymore so long, and then we have to take this means. I think it's a new way to interact with industry.
Thank you.
Yeah.
Nice talk, madam. My question is related to, as we are in the era of energy transition from fossil fuels to renewable energy, and in the renewable energy also only the two sources, when the solar energy as a photovoltaic form and the wind. But the photovoltaic is also going ahead in all. Globally, if you see 50% of the installation is from the solar in the renewable domain. But point is that the solar energy is not uniform throughout the day and the night. So storage is now picking up everywhere. India is also talking about, and right now we have a 130 plus gigawatt is already installed. And now we need a terawatt storage capacity. So how PTV is see this thing, and also the meteorological parameter related to coupled solar and the storage. Is there any plan, or is it something going on?
Yeah, so we are looking at battery storage, and in battery storage is also about battery, let's say, charging and decharging, and the the efficiency in transformation. That is a rather important topic we are looking at. And it's also connected to the electricity grid, because at the very end you put it in the electricity grid and back, and this has to do with stabilization. So in the German system up to now, it's up to the, let's say, more to the small scale to have storage devices. And the question, if you scale the storage devices more, is in the moment not really so much tackled, neither by industry nor by the government. But we see two developments that may change the opinion. And one development is what I said about this mega charging of battery-driven heavy trucks. Because if you have a mega charging unit, it's with a high, high power requirement. And if this mega charging is somewhere in Germany where trucks are driving, it is maybe not there where the electricity grid is stable. And the second development is connected to AI, because now in Germany, a lot of plants are built that are, let's say, high-performance computing units in order to have computing power for AI. And in Germany, it's cheaper to build this on the countryside than in the city. So people now build AI plants, high-performance or computing plants at different areas in the countryside in Germany where also the electricity grid is not there. So you need to think of storage of these electricity requirements, this high hunger for electricity of these two devices that are connected also to batteries. But you also have to think, what is the electricity grid doing? So you could also store in the grid, but if the grid is not stable in these areas where now the high power requirements are, this makes also difficulties. So I think at the moment there's a discussion to build a new, and there's also the plan to extend the energy grid, to have storage in the grid itself, and to look at maybe higher battery-powered institutions. And now there starts, and it will be a law maybe in the next weeks or months, that if you build a new computing plant, you have to take care that you can buffer your energy you need for a certain time, so to have a huge battery beneath. And that's exactly what you said. That is starting now, but it's not as mature as you could expect with all the development that is happening now. And I think it's urgently time to think of it. And sometimes majority is asked rather late what they think of it. But we have our opinion that we think that the stabilization will have much higher requirements, because otherwise you will have extreme values in all this combination of this. It's also a complex system finally that happens, where you have oscillation between different situations, and extreme values might happen like it happened in Spain. And that is something that would be disastrous for different countries in Europe, so we have to look at it. We have a European network on electricity grids where this is all addressed together. So I think at the European value it is the case, but the different governments in Germany and in Europe do not look at it as the same value, and in Germany it's still starting.
So I'll ask one more question, sorry. Right,
There's another one behind you.
Yeah. Thank you. Good morning, ma'am. My question is that in the material science, this as AI is the very much tool is discussing now. So in the microstructure and this micrograph study, it is how much reliable?
So you mean the like advanced materials that are 3D print, or the microstructure like for electronic?
Like microstructure, we take micrographs from ICMT and other microscope and these kind of things.
Yeah. So of course, the measurement of the microstructures at the nanoscale with these different devices like AFM and others is something that is still, it's a relative measurement, by the way, at the moment. But what we are doing at PTB, looking at maybe having this in the range of dimensional measurement. In dimensional measurement, you go to very large scales, like for the wind engines, but you can also go to very nano scales and measure then having rulers or having other things as rulers that can be done. That can be organic materials where we know, for example, the length for it, or it can be other materials where we have a sort of fixed definition of dimensional measurement, so that we can measure then all these microscopic measurement of new materials on the nano and micro scale. But that's right, at the moment the traceability is not there, but it can be done by having sort of new technologies of having dimensional measurement on this scale. That is the way we go.
Actually, my question was related to that. Actually, it's data as a sensor. That's a interesting concept. But then eventually, to use that, would it become? I mean, the access to raw data will be essential. So, will that be a legal metrology issue rather than a scientific metrology?
That's a good question. So we try to advertisement to the government that data is a resource. Some people say it's like the gold of the future. If you have data in order to check, especially digital or AI-based devices, then you have the power also to give the quality. But in the moment, I think it's not yet something that has come to metrology. And this has to do that maybe in digitalization, metrology or some institutions are far ahead, but the whole society is not digitalized. So then data become more important. The data situation, at least in Germany, is that there is a research data infrastructure, it's called. But this infrastructure is really a silo-like infrastructure. There's a research data concept for physics, a research data concept for biology, a research data concept for, I don't know what, for economics. And so in research, these data are some are harmonized in a nutshell from a certain area. But even for researchers to use data from one field for an interdisciplinary other field would at the moment not work because, for example, there's no metadata agreement. So fair data is not really applied there. But then you have the industry, which is not obeyed and has their own data resources. And when we now do the digital calibration certificate, we saw that most industry have their own data infrastructure, sometimes for a long, very long time with old concepts. And in order to have the digital calibration certificate work in a certain industry, we have to make a sort of interface from our format to those to adapt it. And then there's also international activities. And also this German data infrastructure in research does not look at international activities. And so I think maybe that's what we try to do in our forum, digitalization and metrology, that we incorporate many other organizations in order to come to one data format, because otherwise I think data are just something that is spread. And in some countries like the US, data are defined then by companies. And then we should work also for society and make sure that society can participate on it. So I think that's why I said sometimes metrology maybe needs to be louder to the outside, telling, of course, we have tools to assess data. We are the ones that can ensure trust and reliability. But then please also ask us how to organize it in a certain area. And that is something where Germany is still lacking a lot behind, because digitalization is something that is only starting in other administration fields very, very slowly. And that is maybe, if you would be surprised, I saw in India how immigration or others work is very much digitalized, but it's not in Germany. So in a way, this lacking behind needs to be recovered. And at the same time, it's now the time to think of harmonized data worldwide and have also the data, how to say, the data accessibility for everyone, because it can happen that data now then gives a resource that you have to buy from others. And then this will be a trade that might be rather unfair. And we are standing for fair trade.
Hello, ma'am. One more question. Excuse me. When I am using AI for my research.
Where are you? I can see. Okay, thank you.
When I am using my AI for my research, just like ChatGPT, whatever, should I consider it as a tool or a contributor?
A tool.
What is the policy? As it is a contributing, and we should, how can we account its contribution?
So
for our publications, whatever it may be.
So I would say it's a tool, but it's a tool that also is to get embedded in a device, you could say. And then it's a sort of new device that is by these two components. And in order to assess the whole system of the device together with AI, you have to assess both. And I think that's the way to do, because the uncertainty will be related to the AI.
Sorry to disturb you. My question is different.
Okay.
Actually, when I am using AI for my research, suppose I want to publish some work, so should I consider that AI as a tool, just like a Word files on Excel, or we should consider it is a contributing to my research?
Yeah, so this is a
what
question.
What is the policy at Germany
Yeah. So,
at present.
yeah, what you mean is large language models that you use, for example, in research to ask a question or to write a paper or whatever. So we have made a policy at PTB, and also the German Research Foundation has made a policy. So you're allowed to use AI in your research for researching different questions. You have to name it that you did it, but AI can never be an author as a contribution. So it's not a person. So you as an author are responsible also for the AI part you did. So that is one part. And now for metrology. In metrology, also your research might be a research to some fields where you are in a sort of either a very innovative area or in a restricted area. So what we are doing now, we have made strict rules. You can use AI for research like ChatGPT if your research is open. But if it's something that is restricted, we will have an own large language models within PTB, and this needs to be used, and this is trained in a different way, because maybe, as you know, ChatGPT is also trained to remember everything, to grow bigger and bigger in its data and in its learning. So that's why also it's hallucinating, because it has information from different resources from different times and then maybe combines them in a wrong way. That is why you have this issue. And what you can do, you can have a sort of short memory large language model. And if it's short memory, it cannot hallucinate so much, which is important if you have it within PTB. And you can train it, for example, for always, reproducing questions. Like if you have a conformity assessment, you ask the question, is that data that you get the ones you need for conformity assessment from an industry? And these questions are repeating, and then you can have other structures of large language models. So what we do in PTB, creating our own internal large language models to use it. But on the other hand, having a sort of, lightning system, like allowing PTB people to go to outside large language models, and there are many. And some of them are more, let's say, vastly using also data you don't know the resources from others. So we have green light, red light, and orange light, which ones you can use for which purposes. And we have regulations done in PTB. They're combined with training, and train everybody at PTB how to use this AI in your research. And I think it's rather important to get awareness, have rules, and then have, for the legal metrology or others, have your own, let's say, cloud or your own activities within the barriers of the metrology. And that's also something where we need to translate, or transform our own way of using large language models as AI. That's right.
Thank you, ma'am, for the wonderful presentation. And your address had truly inspired us and given us a visionary perspective on the future of global metrology, and to express our deep gratitude and appreciation for your enlightening lecture and your gracious presence with us today, may I request the entire audience to kindly rise for giving ma'am a standing ovation, please. Thank you so much, ma'am. Now I request Dr. Meisner and Dr. Venugopal Achanta to kindly join us on the dais. So as a token of our deep appreciation and respect, now I request our director, sir, to please present a shawl to ma'am. In Indian tradition, presenting a pashmina shawl is a gesture of honor and warmth. Just as metrology weaves precision, traceability, and trust into a coherent system, this finely woven pashmina symbolizes strength through refinement and continuity through generations. Along with the shawl, we also present a memento as a mark of our gratitude and remembrance of this significant occasion at CSIR-NPL. Thank you, ma'am. Now I request Dr. Uwe Meisner, Head of International Cooperation at PTB. Thank you, sir, for joining us here today. Thank you, ma'am. Thank you, sir.
We have two questions for you either. One is about the history of PTB, and this reflects our long-term cooperation. And you may open it to have a look at it.
Thank you, ma'am, for the kind gesture.
So it's a plate, and this is the sign of PCR. First thing that they did, the gate at the new Metrology Institute, 1887 in Berlin, and this is the sign of the name. And here is a present that reflects the modernity or the future of our activities, and it's something that looks into the future. So it's a present to look at the technology. Yeah, it's lots of things to take it away. So it's a sort of plate, and then you have a wafer, and on this wafer it's engraved the electric triangle and an electric quantum measurement. So you can put this in there and have a wafer that displays our new methodology.
Ladies and gentlemen, while we have just expressed our appreciation through a traditional felicitation, we now move to a moment of academic distinction and institutional pride. It is indeed a matter of great honor for us that we have Dr. Denz with us here, and we are happy to confer MSI Honorary Fellowship, a recognition reserved for individuals who have made outstanding contributions to the advancement of measurement science and international cooperation. Before the formal conferment, I request Dr. S.K. Jaiswal to kindly shed light on the MSI and the significance of this prestigious fellowship. Sir, please.
Good morning to all of you. I would like to tell very briefly about the Metrology Society of India. It is a approximately 42 years old society which was formed on 14 December 1984 to promote the metrology and its vivid aspect. And Metrology Society of India operates its activity through the Executive Council and General Body meeting. And we have 4 regional chapters in India and headquartered at the MSI headquarters in Delhi in NPL. And MSI is organizing various type of conferences, workshop, training, colloquia, and so many activity to promote and disseminate the metrology. And Metrology Society is publishing a quarterly journal called MAPAN, Journal of Metrology Society of India, since October 1985. So our journal is roughly 40 years old, and it is the best journal in Asia Pacific region, having impact factor of 1.3, and lot of editorial board members are from abroad. I am happy to inform that Dr. Cornelia agreed to become our board member. So, thank you. Thank you for that. And MSI is also the part of the member of the IMECO. I met Dr. Frank Hartis in Czech Republic and also in APMP. So he was vice president of the IMECO. So MSI is the member of IMECO, and we are promoting for metrology at the global level. So we have shake hands with the IMECO for that purpose. And MSI has more than 2,300 members, which are the life members, associate members, corporate members, student members. So there are various category of the members, but one of the most important is the fellow member. And honorary fellow, we till now we have only given 25th. So today is 26th fellow member in 41 years history of the MSI, and by definition, honorary fellow shall be an individual of outstanding professional distinction in the field of metrology. For her admission will be conducive to the best interest of society and shall be only enrolled by invitation of the council. So such enrollment may not exceed 5 per year, and total number of honorary fellows shall not exceed 5% of total membership. So in our executive council meeting held last month, it was decided to confer you honorary fellow of MSI. So thank you for accepting us.
Now I request President of MSI Society, Dr. Venugopal Achanta, Vice President, Dr. S.K. Jaiswal, Vice President, Dr. Shankar Agarwal, to please join on the dais to confer the honorary fellowship to ma'am. Ma'am, please. Thank you, ma'am, for accepting this, and it is indeed an honor for MSI and NPL to recognize your distinguished contributions to the global metrology community.
Cornelia has become new, so she has to join the new territory. Sometime I will attend the admit conference. So not conference, but at least you are in NP. That's right. Yeah.
Thank you, ma'am. And now I request Dr. Uwe Meisner, Head of International Cooperation, Asia, to kindly share his thoughts. So please.
Thank you very much. I didn't prepare any speech, but thank you for just allowing me to speak on behalf of PTB's Technical Cooperation. And I would like to thank you, everybody, for your cooperation, for your friendship and partnership in our cooperation, both on a bilateral level. As you may know, PTB and NPL had a long journey in bilateral technical cooperation in many different fields. Recently, it's PV, as you may know, and it's also water monitoring, Ganga River. But also we had a regional intense collaboration on a regional scale in the SAARC region, where also NPL scientists and colleagues have been instrumental to strengthen capacities in your neighboring countries. And for this also PTB is very much grateful. We do look forward to continuing our partnership in both levels. And again, thank you very much. For the younger ones of you, please get engaged, become engaged. I think it's really a worthwhile journey, I would say, and a great experience. And again, thank you very much, for your partnership. Thank you.
Thank you, sir. Once again, we extend our sincere gratitude to Professor Cornelia Denz and Dr. Uwe Meisner for their gracious presence and for strengthening the enduring collaboration between CSIR-NPL and PTB Germany. We also thank our director, distinguished dignitaries, and all the participants for being part of this significant occasion. The future of measurement is not built by instruments alone. It is built by institutions that trust each other, by scientists who collaborate across borders, and by leaders who dare to envision transformation. And Professor Cornelia Denz, we thank you for strengthening that chain today. And just as traceability preserves moments of scientific community and certainty, a photograph preserves moments of scientific partnership. And today's gathering represents another significant link in the enduring collaboration between CSIR-NPL and PTB. So may I now request all our distinguished dignitaries and our participants to kindly join us outside the auditorium for a group photograph.